Okay. Okay, so let's discuss the problems we had in the JetBrains Academy YAF challenge coding part. So we had 8 problems. The first problem called turns and coins. So what we had in this problem? We had a sequence of cells. In each cell, we may have a coin or we may have spikes. And what we can do, we can go from left to right every time we jump 1 or 2 cells forward. And we need to calculate the maximal number of coins we can get. It was quite easy problem. So how do you solve it? Basically, you find the leftmost position when you have 2 spikes in a row. And when you have 2 spikes in a row, you cannot jump over them. So you cannot go to any point to the right from this position, but you can visit all the cells from the left from this position. So the answer will be just the sum of all coins to the left from the leftmost position when you have 2 spikes in a row. And if you don't have 2 spikes in a row, then you just can visit all the cells with coins, so you can collect all the coins in the input. So that's also this, like the first problem. It was quite easy, just warm-up problem. I hope everyone solved it. Next one. Next one problem was a little bit more difficult. So what we have in this problem, we had 2 numbers, n and m, and our job was to build a flight network. Flight network should contain n cities and m flights. Every flight connecting 2 cities. And we need to build this network in such a way that the sum of all distances between every pair of the cities is minimal possible. So how do you solve this problem? No, I believe the hardest part of this problem was to understand the statement. So statements was kind of complicated. So you need to build some flying network. You need to understand what is network, what is distance, what you need to minimize. But as soon as you understand what you need to build, the solution is pretty straightforward. So what we do, let's look at the distances. So the distance may be 1 only if 2 cities are connected with direct flight. So if we have direct flight, then we have distance equal to 1. For every other pair that doesn't have direct flight, the distance would be at least 2. And the idea of this problem is that you can actually make all other distances equal to 2. So you know they're at least 2, but it's always possible to make them equal exactly 2. And you do it by just connecting everything to the first city. So you first build n-1 flights from the first city to all other flights, to all other cities. Now the distances from every pair of cities is at most 2. And now you just add basically random flights from any pair of cities, and every additional flight will decrease the total sum by 1. That's all. So that's the whole problem. So again, if you understand what you need to build in this problem, it's then pretty easy to get the optimal solution. But yes, maybe this problem statement was a little bit more complicated. Problem C. Problem C was card game. Problem looked like this. We have some set of playing cards, just normal poker playing cards. We have 4 suits. We have 13 possible ranks. And one suit is special. It's specially selected to be a trump suit. So we have 3 normal suit and 1 trump suit. And we define some rules how one card can beat another card. We say that one card can beat another card if they have the same suit and one card have higher rank, or if one card is a trump card, another card is not a trump card. So trump card can beat any other card. And yes, and card of the same suit can beat highest card can beat the lowest card. The question was to split all the cards into pairs in such a way that in every pair, one card can beat another card. No, how we do it? Let's do it like this. Let's sort all the cards of every suit. So if I take every suit, sort all the cards by the rank, and then in this order we can split them into pairs. Since they have the same suit, one card will beat another card. Now from every suit, one card will remain. At most, one card will remain. If we have even number of cards, we have no card remains. If we have odd number of cards, then one card will remain. Now we will take these remaining cards and beat them with some trump cards. if we don't have enough trump cards, then there is no solution, obviously. Yeah. Now we have some remaining trump cards. Again, sort them by the rank and assign them in pairs, like from left to right. That's all. Solution is pretty easy, but the problem itself is pretty technical. So you need to decode the input, find these ranks. So again, you need to sort cards by their suit. Then inside each suit, sort them by the rank, and so on. So it's pretty technical, but the idea of solution is pretty simple. So this problem was mostly for people who like programming, not math. So not a lot of math in this problem, but a lot of programming. You made a lot of, you may find a lot of interesting tricks to make your solution easier. For example, when you want to compare cars by the rank, it's easier to first move from the ranks to numbers. So assign each rank some number from 0 to 12. Yeah, in my case, from 0 to 12. And now you can do it by doing something like this. You have string of all possible ranks. Now to find the to go from the rank to its number, you just find the index of this character in this string, and vice versa. If you want to find by the number, you need to find the corresponding character. You just take corresponding character to this index from this string, and so on. So it's problem mostly about programming and about how to carefully implement what you need to implement. Okay. Next problem is much less trivial. So final countdown is problem. What you have in this problem? We have a big counter, and this counter is just counts down from its initial state to 0. So every time it decreases by 1, and the time it takes to decrease it by 1 depends on number of digits that change. So every change of the digits takes 1 second, and we need to calculate total number of seconds before the counter reaches 0. So how do you do it? No, there are multiple ways to do it, actually. Let's do it like this. Let's look at the initial state of the counter. There is some number displayed on the counter initially. So for example, let's say it's 568, like here. Yeah. Let's calculate how many times each digit will change before the counter reaches 0. So the last digit, the rightmost digit, will change every step. So every step, the last digit will change. So total number of changes of the last digit will be 568. Now the second digit will change only when number of tenths changed here. So it happens 56 times. Okay. And the first digit will change 5 times. Okay. So to calculate the final result, we need to calculate this sum, like 568 plus 56 plus 5. And you can actually do it. So in Python, you can calculate it like this. You take number n, every time you divide it by 10, and so on, and to calculate sum of all these numbers. Unfortunately, if you do it in Python like this, just using this formula, the solution time complexity will be not linear. So it looks like linear because you have linear number of additions. But these additions, every time you calculate sum of two very long integers. And when you calculate sum of very long integers, it's not fast. Yeah? So sum of two long integers takes actually linear time of digits of this number. So the solution will pass some test. It will give you some points, but it will not give you the full score. So to get the full score, you need to make some more observations. So let's look at this sum again, like this: 568 plus 56 plus 5. Let's split it into parts by each power of 10. So what will happen in this sum? We will have 100 multiplied by 5, then 10 multiplied by 5 and 6. So because it's from first and second sum of the sum, yeah? And 1 will multiply by 5 plus 6 plus 8. Now, this form is good because it kind of looks the same like you have when you have a string of digits. So if you represent number as a string of digits, you also have each digit multiplied by some power of 10. So basically, these numbers 5, 5 plus 6, and 5 plus 6 plus 8 are the digits of our answer. Yeah. So we go from left to right. Leftmost digit is 5, like 5 plus 6 is 5 plus 6 plus 8. And a good thing is that we can calculate these sums in linear time. So these sums are just prefix sums in the array of digits, we can calculate prefix sums in linear time. Now, these sums are almost what we need to get. So these sums are the digits of our final result. But the problem is some of these sums may be greater than 9. Yeah. So what we need to do, we need to go from right to left in this array and carry the bits from right to left, like we do when we calculate like sum of big numbers or anything else. So when you multiply by big numbers. So if you know how big number arithmetic works, it works like this. We first do something and then try to finalize the result by moving these extra digits from right to left. Yeah. So for example, in our case, I have these sums 5, 11, and 19. So I go from right to left. I take number 19. It's greater than 9. So I take this 10 from this number and move it to the left. So I leave this 9 here and move this 1 to the left. So I get 12. And then I move to this 12, get this 12. Again, you divide it by 10, take the remainder will be 2. So you move the 2 in this place and move all the remaining digits to the left. And in the end, you will have all digits not greater than 9. So you have the final result. That's all. That's like the full solution. So the time complexity of this solution will be linear because I can calculate. All my operations only use small numbers. Yeah. So I only calculate sum of digits. Sum of digits is not greater than like 9 multiplied by the length of the number. So all the numbers I'm operating with are very small. So first I calculate prefix sums, and then I perform this carrying bits from right to left. Both operations work in linear time. That's all. That's the full time. That's a full score solution. Any questions? No? Okay. Let's move to the next problem. Next problem called feed cats. It's a little bit more, I would say. Okay, so for some people who know dynamic program, maybe a little bit more standard problem, but it's still I think it's nice problem. So what we're doing here, we have some set of cats. So each cat represents some segment of our. So I have basically I have n steps, and every cat represents some segment of these steps. Yeah. What I can do, in some steps, I can feed all the cats. So what will happen? I will feed all the cats that, so this segment contain my step. Yeah? So I can feed all the cats. I can feed them partially. I only can feed all the cats that are presented now. Yeah, and restriction is I cannot feed the same cat twice. So I need to feed some cats, but I cannot feed the same cat multiple times. And the question was to find the maximal number of cats I can feed in this model. So, for example, in this picture, I have these 2 positions when I feed the cats. First time I feed these 3 cats, like this marked blue, and the second time I mark these 2. I feed these 2 cats marked red. Yeah. So how to solve this problem? No, we can solve this problem using dynamic programming. Let's say that dp of I is the maximal number of cats I can feed if I only allowed to feed in the first I steps of my process. So how can we recalculate these values? No, let's look at the final step. Let's look at the step I. What will happen in step I? There are 2 possible cases. I can feed the cats or I can not feed the cats. If I don't feed the cats in step I, then the result will be the same as dp I minus 1. Okay? Because if I only allowed to feed the cats in steps from 1 to I, and I don't feed the cats in the step I, I'm only allowed to feed from 1 to I minus 1. So answer is the same as dp I minus 1. If I feed the cats in time I, then we can recalculate the result. How can we recalculate the result? Let's calculate number of cats are present in moment I. Let's say sum I is the number of cats that are present in moment I. So I will feed these cats, plus I will feed some cats to the left. And these cats to the left should be fed in steps before left of I. Where left of I is the leftmost segment that contain position I. So for each position I will find the segment that contain position I with the leftmost left border. And if I feed cats in position I, then the previous feeding time should be before this position left of I. we do. Okay. Now, if I know the values sum I and left of I, then I have linear time dynamic programming. Yeah. So every time I calculate dp of I have two options. I take maximum of them. I have linear time dynamic programming. Now, how to calculate values sum I and left of I? No, there are multiple ways to do it actually. So you can calculate sum of I using some prefix sums, or you can do it using segment trees, or basically anything else. So it's easy to calculate sum of I in linear time actually using prefix sums. Calculating left of I is also doable in, I believe it's doable in linear time, but it's much easier to do it in log n time. You can do it using segment trees, you can do it using sets. So you can go from left to right and maintain the sets of the segments that intersect you right now. And then every time you take the minimal out of this set. So C++ sets will allow you to like add elements, remove elements, and find the minimal element. So in all operations in log n time. So you can do it in n log n time complexity. And that's all. So the total time complexity of this solution will be n log n. Any questions? No? Nope. Okay, let's move next. Okay, next problem is tricky. So the next problem is called Battle with the Galactic Empire. Again, this problem had very long problem statement. You need to understand what's going on there. So I'll describe you it briefly. So what's going on in this problem? You have some AT&T machines, and each AT&T machine have 4 legs. And these 4 legs are like in the corners of the square. In each leg can be stable or broken. And we will say that machine is unusable, yes, if it has two adjacent legs broken. And what we do, game goes like in 2 steps. First, we break some legs, at most k legs, and then our opponent, like Galactic Empire in this case, will fix some legs. So it can fix at most L legs. So we have these 2 numbers, k and L, number of legs we can break, and number of legs they can fix. And what we need to do, we need to maximize the number of unusable machines in the end. So if you assume your opponent will play optimally, so it will fix at as many machines as they can. So we want to maximize the number of broken machines in the end. How we solve this problem? Okay, let's do it. So first thing you need to notice is there are 6 possible states of the machine. So we can make machine with 0, 1, 2, or 3 or 4 broken legs. But machines with 2 broken legs can have 2 types. So we have machines with 2 adjacent broken legs, like type 2b, and 2 non-adjacent broken legs, like type 2a. The difference between 2a and 2b is that type 2a is stable and type 2b is unstable. Yeah. So they both have 2 broken legs, but one of them is stable, another is unstable. So first thing we'll do, we will read the input and calculate, count the number of machines of every state. Yeah. Now, instead of like this array of machines, we just have 6 numbers, number of machines for each type. Now, first, let's think what will the empire do? So what will the second player do? So imagine you are an empire, you have some machines. So you need to fix as many as possible, and you only can fix up to L legs. So what we will do? There are some machines that can be fixed in one operation. Yeah. So machines of type 2b and 3 can be fixed in one operation. And machines of type 4 can be repaired in 2 operations. So if you want to maximize number of machines you fix, then you will first fix all the machines that can be fixed in one operation, and then fix all the machines that have been fixed in 2 operations, if you have any operations left. Yeah. So that's what the second player will do. Now, when we know the strategy for the second player, what we need to do? We want to perform some operations. These operations will create some machines that are fixable in 1 or 2 operations. Yeah? And depending on number of machines fixable in 1 or 2 operations, we know how many machines the second player will fix. So we know the final result. So what we'll do? Let's look what we actually can do as the first player. So we can break some legs. When we break leg, we move the machine from one state to another state, like using this diagram. So from 0 legs, we go to 1 leg, from 1 leg to 2 legs. No, we can go from 1 to 2a, but it's obviously never optimal. Yeah. If we can break another leg, we can always break the leg adjustments to all of the broken leg. Yeah. So these are all operations we can do in one step. Now, we know that we make some machines breakable, repairable in one operation, and some machines repairable in two operations. So let's fix the number of machines repairable in two operations. So number of machines of type 4. So if we know how many machines of type 4 we want to create, so we can do it. We can create these machines of type 4 using very simple greedy algorithm. So first, we will break all the machines of type 3, then all the machines of type 2A, then machines of type 2B, then machines of type 1, then machines of type 0. It's easy to see that you need to do it in this order because, okay, I'll leave you to as an exercise. It's actually true. You can do it greasily in this order. It will always be optimal. So you can look at any other sequence of operation that produce the same number of machines of state 4 and just prove that you can do the same with performing operations in this order. Now, when we make enough machines of type 4, we need to maximize number of machines that are broken but fixable in one operation. So number of machines of type 2B and 3. And we again can do it using simple greedy algorithm. So we first break machines of type 2A, machines of type 1, and machines of type 0. So we can do machines of 2A and 1 operation, and machines with type 0 we can break in 2 operations. So we just maximize number of broken machines using these operations. And that's all. So now we can iterate over all possible values of x. So we first fix how many machines of type 4 we get in the end. Now, if we fix number of machines of type 4, we can simulate this process in constant time. So every time we just break all possible machines from this type to this type. So we have like, let's go back. So we have like five steps here. Every step can be made in constant time. So we can simulate this whole process in constant time for every fixed value x. And now what can we do? We can simply iterate through all possible values of x. There are at most n possible values of x. For each value of x, we simulate this process, calculate number of broken machines in the end, and get the maximum out of them. Like total time complexity will be linear in this case. Any questions? Nope. Okay, this was very tricky problem. So it's not very standard. It doesn't use any standard algorithms. You just need to basically research what's going on in this problem and then find the solution. Good. So we have 2 problems left. Let's go. Problem G. Problem G was called moving platforms. So what we have in this problem? We have basically a graph. So we have some platforms and some passages between these platforms. And these platforms are moving. And so we only can move from one platform to another if they have the same level. So each platform has some level assigned, so just a number. And we only can move from one platform to another if they have the same level. Now, after every step, the levels will change. It will change by this simple formula. So if every level will be increased by this value Si modulo h. Basically, you go in cycle modulo h every time you move like Si positions to the right in this cycle. And the question is to find the basically shortest path from one node to this. We find minimal number of steps we need to go from the first node to the last one. Well, it's actually a pretty standard problem. It's technical. It requires a lot of knowing of algorithms, but pretty much standard. So what we do? We use simple Dijkstra algorithm, the same one we used when we just find the shortest paths. So how the Dijkstra algorithm works? We calculate the shortest distance to every node. In our case, it will be minimal number of steps we need to get from first node to node I. And every time, like Dijkstra works, we take the minimal value of di and try to make transitions from this node to all other nodes, and so on. Every time, take the minimal element, make transitions from it, and so on. So how to make transitions? That's the tricky part. So to make transitions, we need to find the closest moment when two platforms have the same level. How do you do it? No, you need to solve this equation basically. So you need to find minimal t such that here in the left I have the level of the first platform. In the right I have the level of the right platform. So this is just the equation that two platforms have the same level. Now let's transform this equation. So what we have in this equation, I will just transfer this ln in one part, this s in another part. So I have the equation like this. And then I will say that the something equals to 0 modulo h is the same. It is equal to some x multiplied by h. Then after some transformation, I have this final equation. This equation is called the de-Fontaine equation. So it's pretty standard equation. You need to find integer solution for the equation like this. So it's linear equation of two variables, and you need to find any solution of it. In my case, I need to find minimal positive solution for t. So you can solve the de-Fontaine equation using the Euclidean algorithm, and then like de-Fontaine equation have multiple possible solutions, but they are periodical. So I have some periodical values for t. I need to find in this period, I need to find the minimal non-negative value. You can find any value, find the period, and then just take this value modulo this period, and you will find the smallest non-negative value. So it's pretty technical. You need basically know some algorithms. You need to have a lot of technical skills to implement them, but overall problem is pretty standard. Any questions? Okay, the final problem. The final problem called visit them all. So what we have in this problem, we have some graph, and this graph has n nodes and n edges. So this is a very specific graph. It's a connected graph that have the same number of nodes and edges. And in this graph, we need to find the shortest path that visits all the nodes at least once. Like in this case here I have this this red path actually visits all the nodes of my graph exactly at least once. Yeah? So I need to do it in minimal number of steps. First of all, let's see what graph we have. So we have a very specific graph with n nodes and n edges. It's almost the same as a tree. So in tree you have n nodes, but n minus one edge. So it's almost the same, but one more edge. Yeah. So let's first solve the problem for the tree. So what's happening if you want to visit all the nodes of the tree? The way you do it, you start from, if you fix the starting and destination point from your path, and try to visit all the nodes of the tree, you will actually see that you visit you walk through every edge twice, except the edges that belongs to the path from S to T. So the answer will be 2n minus 1, because I have n minus 1 edges, minus the distance from S to T. And to minimize this sum, I need to maximize distance from S to T. So the problem is just to find the two nodes with maximal possible distance in a tree. No, it's just problem of finding diameter of the tree. It can be done in linear time. Now let's move to our problem. Now problem, we don't have a tree. We have something else. We have graph of n nodes and n edges. It's not a tree. It's like a cycle with some attached tree. So a little bit more complicated structure, but it's very close to the tree actually. So we will use very similar algorithm to this problem. Now let's see. So we need to visit all the nodes of this strange graph. Let's see when we again, we have some two nodes where we start and finish of our path. So some nodes S and T. So if this nodes S and T belongs to different trees of this graph, so I have cycle plus some trees. So if S and T belongs to different trees of this graph, then the optimal path will always look like this. So I start in vertex S, then visit all the nodes inside this tree, go to the cycle, go around the cycle, visit all the nodes in every tree I visit, then go to another tree that contains node T, visit everything there, and finish in the node T. And it's easy to see that I actually picture is kind of similar to what we had before. So I visit every edge twice, except one edge that I didn't visit at all, and except all the edges on the path from S to T, and I visit every edge from S to T once. So how do you calculate the answer? The answer will be 2n minus 1 again, minus distance from S to T, minus this length of this path from S to T. And the length of this path is actually di plus dj plus the difference between j and I. So if these two nodes belong to trees I and j, then the distance between them will be depth of the tree I plus depth of the tree j. So it's these parts of trees plus this distance around the cycle. And distance around the cycle will be just j minus I. Now, we can pre-calculate all the depths in linear time. So for every tree, let's calculate the maximal depth in this tree. Now, how to find the maximal sum, minimal sum like this? Now, when we want to minimize something like this, again, 2n minus 1 is the constant. So to minimize this sum, I need to maximize di plus dj plus j minus I. And you do it like this. When you want to maximize something like this, you split this sum into two parts. One part containing I, another part containing j. So in my case, I have this like I have di minus I plus dj plus j. So left part contains only I, right part contains only j. And now you simply, again, the constraint is that j must be greater than I. So for all pairs j and I, so such that j greater than I need to calculate maximum sum like this. So you do it like this. You iterate all positions of j. For every position j, you need to find the position to the left from it with maximal difference di minus I. No, you can go from left to right and maintain current minimum for maximum for all nodes you visited before. So you maintain this current maximum, take the node j, take the minimal possible node, maximal possible node I, calculate the sum, over all the sum, calculate the maximum. That's all. That's how you will maximize this sum. And again, the time complexity of the solution is actually linear. So I just go in from left to right, and every time I calculate the maximum out of these values. Okay. Okay, that's not all. The second case is when these nodes S and T belong to the same tree. The nodes S and T belongs to the same tree, then an optimal answer will look like this. So it's similar, but not exactly. So what will happen here? I visit all the edges twice, except two parts, except the cycle. All the edges on the cycle will be visited only once. And except the path from S to T. So my answer will be 2n, because total number of edges is n. So I walk along each edge twice, minus c, because I visit all the cycle only once, and minus distance from S to C. Now, n is constant, c is constant, so I only need to maximize distance from S to T. But again, it's the problem we solved before. So to maximize distance from S to T, I just need to find the diameter of the graph. You can do it in linear time. So you find diameter of each of the trees, find the maximum out of them, and that's all. Then you can have minimal possible sum. And then you check these two cases when ST belongs to the same tree, and then they belong to different trees, and calculate the maximum or minimum out of them. And it will be your final result. Both cases can be solved in linear time, so total time complexity is linear. Any more questions? No? Okay, that's all. That's all the problems we have this year. Thank you for joining us, and see you next year.